This is James Burke. This summer I worked with Dr. Chris Depsick and Dr. Edward Peltier on a dry biomass burner and measuring emissions using different types of dry biomasses. And we developed a lesson that we could try to simulate this in our classroom and allow students to research different biomass fuels. We started by making different pellets. We actually used some coal from a local power plant, some ground algae, and some white pine. We did use some cornstarch to get them to stick together, and this was a pellet press that we used to smash the pellets together. These were the pellets after we dried them in the oven. This was the base of the burner, and we could control how much air was going into this. These were thermocouples that would measure the flame temperature at different heights in the flame after we covered it up. This is a window that we could actually watch the burn happen, and this was our group inside of the um, engine test room. These were taking the exhaust outside, and this is our burner right here. You can see the burn happening. I've also had smoke meters and different things. We also used a bomb calorimeter to measure the energy content of each of the different types of fuels alone that we were using. So we measured coal, algae, and white pine separately. And these were the energy contents in BTU per pound that we got for coal, algae, and pine. You can see that the coal and pine have a lot more energy available than the algae. This was carbon, hydrogen, nitrogen analysis of the same different fuels, the blue being coal, and coal had more carbon, which we would expect, than the algae and pine. The algae, the red bar here, had a lot more other inorganics in it, which limited how much of it burnt away and how much of the ash remained. This was a 100% pine burn. This shows the gas concentration, the carbon dioxide, and it went way up real fast. This time scale here is actually a lot shorter, and it got up to 60,000 parts per million. The 50-50 coal pine and the pine coal algae mix burned much slower. You can't really see it on this graph, and they didn't release near as much carbon dioxide in the amount of time, probably similar over the range of the burn, but the burns drug out a lot longer. This shows the different burn profiles on the same time scale. You can see the pine, the blue one here, burnt really fast. The red one was the pine coal, how its burn profile worked out, and then the pine coal algae mix there as well. So for our lesson, we wanted to look mainly at the carbon cycle and develop a burner that would work similarly. We have a diagram of it over here. We used coffee cans, a cigarette lighter that we bought at Walmart, the replacement for your car. We had a digital thermometer and a pop can, a small pop can with a water sample. And we made a window out of a flashlight so we could watch the burn happen. And we used a tire inflator in this Ziploc container to be able to pull the exhaust, pull the air out, and we had a filter up here. We could see how much smoke was coming out, and we were bubbling it through and trying to measure carbon dioxide emissions the same way. So I'll go through each of those. There's another group that's going to present their lesson on this. We used a bromothymol blue solution, and we could breathe into it and turn it more acidic as carbon dioxide dissolved in the water, which would change the indicator to yellow. And then if you put some algae or Elodea plant in and gave it some light, it would pull that back out and turn the solution to blue, showing the carbon came back out. So we wanted to use the same method to show carbon fixation as we were using in our measuring carbon output from our system of combustion. We did a titration, and in the titration, it starts out blue and works its way across to yellow as we added carbon dioxide from Alka-Seltzer. I have some pictures and quick video of my students doing this titration part last year. It was something we'd worked on the year before. Worked out really well. We had a pH sensor and a test tube and some Alka-Seltzer, and they would mask the Alka-Seltzer, the test tube, and in this case a graduated cylinder they're using to hold it up, and then they would sped this up a little bit. You can see the bubbles going through there. That's carbon dioxide, and the mass of the test tube in the water and the Alka-Seltzer will drop by the amount of carbon dioxide that's being bubbled through our system. So we could get a known pH change, and we're watching the pH change, and they would create a graph little titration curve. You can see the color actually changing above that. You have to stir it a little bit when it gets done bubbling to get your pH to stabilize. We stirred it with just the tubing and this little red cap we had in here. Okay, so here's the mass after they bubbled that, and the amount that they lost was the amount of carbon dioxide they bubbled through. They'd record their pH. This was their data table, and you can see on the right side they have the total carbon dioxide that they had added, and then their pH of their solution, and that's a saturated lime water solution. You can see here at the beginning they start off at 12.7 and 12.82. That's a big difference in pH when you get that high. So their graphs were off a little bit, so you need to start with the same pH, or at least know what it would take in carbon dioxide to get those to change, and your curves will line up. This was the one we developed this summer. So we have the blue up at the top and then change to yellow about where that would occur. And in the first about 0.6 grams of it, we ended up with a pretty linear relationship, and we could use this mathematical formula right here with the slope and y-intercept. That's our pH at the beginning, and our slope for every what our rate of change of pH was as we added grams of carbon dioxide to the system. So we could estimate pretty well. This is a video of our, back up here, video of our burner in time lapse, and you can see we have a sample in here. We used a 12-volt power supply to start our cigarette lighter. We left that on for 200 seconds on max, and this is also the tire inflator. You can see the smoke filling up in here a little bit, and it's bubbling this through our system. And you can see that it started out blue. It's going to change to yellow here by the end. I believe we had a charcoal sample, which we're using for our analog for coal in this setting. I recommend doing this in a hood if it's available. Outside, you can try some samples and see how much exhaust you're getting in your setting. So this was our carbon dioxide when we estimated it using our graph, and our charcoal and pine again were much higher than our algae, which would make sense. It correlated with what we got in the burn data. And then we also had this where we would, during the same burn, we were monitoring the temperature change of we put a 50-gram sample of water in our can, and then we would turn on our lighter down here and light it, and the can temperature would go up and then taper off as the flame went out. And we could watch the burn happen in here, but again, we wanted to turn that off at 200 seconds, the lighter off at 200 seconds, and then our stats on from Logger Pro would give us a change of water temperature here at 12.6. So we graphed our different fuels, and if you notice on the right side, we have one with no fuel because our lighter is adding a significant amount of energy. It was changing at about 7.5 to 8 degrees with no fuel being added at all. So we use that as our baseline, and the temperature change in the other samples we assumed was due to the fuel that was sitting on top of the burner, and we could compare those. We wanted our students, the main engineering design here is to design a fuel type that would burn the cleanest, produce the least amount of particulates. We have a coffee filter in there. You'll see in the lesson part that we were actually seeing how much smoke we could filter out in different particulates. But they could burn about anything, any dry biomass. We had Traeger pellets, pure charcoal pellets. We mixed some pine algae, very similar to what we did, but you could burn corn cobs, corn husks, any dry biomass, paper pellets. And we wanted students to do a life cycle assessments on their biofuel, kind of looking at how sustainable the harvesting of that material was, how easy it was to get back. If there's any processing involved, like in ethanol, there's a lot of water use, which is a major drawback, and then the energy involved in processing it, and then how much energy you could actually get out. And then in the end of life here, we were more concerned about the emissions, what types of things were being given off. In the case of coal, actual coal, you're getting off a lot of mercury and heavy metals that aren't good for the environment, and trying to mitigate those. The last thing we wanted our students to do was present their fuel type, their biomass pellet, to pitch it to a Shark Tank, to an authentic audience, and try to get somebody to buy their type of fuel and answer questions from their life cycle analysis. So that's our video. Sorry it was a little long. Thanks for watching. In the comments, I will link the burner directions and try to get a link to the other group's lesson on